Well, hello everyone, and welcome back to Adrian's Digital Basement 2. On today's video, it's just a little casual thing again. This is the power supply that came out of that Agfa Compugraphic 9000 PS. Very interesting video. It's on the main channel if you haven't seen it, but this obviously is just a normal AT power supply. This one's made by Astec, and I didn't do any kind of testing of this in that video because since it is just a normal AT power supply, I could use one of my normal bench power supplies to test that machine, which is exactly what I did. But I like this power supply. This is a high quality power supply, and this is perfect for using inside a computer like the IBM PC 5170, which I keep on the bench all the time. That one I'm pretty sure has its original power supply, but it's always nice to have a spare one of these. And these large form factor power supplies aren't exactly common anymore. So in today's video, I want to open this thing up, take a look inside, and then I want to show how I'm going to test this. And I'm going to be using this to do that testing. This is an electronic DC load, which I got before all the US tariffs hit. That way I could save a little bit of money. And I just need to connect this power supply up to that. That way it can simulate some 5 and 12 volt load on this power supply. And we can see how the regulation is on this and see if the caps are in good shape and everything like that. This is an Astec power supply, so I'm presuming it should be really good quality and almost certainly just work. I sometimes get emails from viewers asking about tips and tricks on troubleshooting power supplies. And I gotta say, I am far from an expert on power supply repairs. I've obviously done some amount of it on the channel, but before I even open this thing up, you do have to be careful that these labels are real. This thing does have dangerous voltages inside, especially if it's connected up to the mains, which is, right here. It's there. And if you have it set for 240 volts and you're in a country with 240 volts, then yeah, the voltages you're going to see inside of this thing, 300 almost up to 400 volts. And of course, there's a lot of power behind the mains connection, so it can be lethal. So you got to make sure if you're going to operate this thing with the cover off, you know how to do so safely. If you are going to test one of these without opening it up, that's fine. And you can use something like this DC load, and that is safe because obviously this box is where all the dangerous stuff is inside, and everything that comes out of this power supply is just DC low voltage. Therefore, there's really no danger other than the fact that if you don't open this thing up to at least look inside, you never know if something is broken in there or there's like screws floating around that could short something out, and that could be bad. Luckily, of course, this thing is designed to fail in a way that should be safe in this metal box. So yeah, just word of warning, don't open these up again unless you know how to do so safely. And obviously with it unplugged and it's been off for a long time, like this has not been used in forever, then pretty much you can be sure that everything's gonna be safe in here. It's just, yeah, if you've turned it off recently, then some of the caps can still be charged. And then of course, if it's plugged into the wall while you have the cover off, that's where it's the most dangerous. Okay, safety stuff out of the way. So as I mentioned, this is an Astec model AA14220, made in Malaysia. It does have dual voltage input. It is rated for only 200 watts, which is kind of ridiculous, isn't it, for something as big as this? Only 200 watts, but yeah, this was back in the day. Date code 1989, 12th week. So yep, power supplies were just not as efficient as they are these days. Not to mention, it doesn't have anything like power factor correction and all the fancy circuits that new power supplies have that can make them smaller and more efficient. And of course, when you're more efficient, less heat, and you don't need as large of a case and as large as a board because things don't get as hot. As I was saying, I get emails from people asking for help on checking power supplies. And one of the most important things to keep in mind is that with old power supplies especially, they often don't regulate properly when there's no load. In fact, the IBM PC 5170, just sitting right over there, that thing's notorious because it came out in 1984, and the original power supply in that thing, it was designed to have a hard drive as a load. Full height, large hard drive, lots of 12 volt load on that, plus some 5 volt load. The power supply in there was designed for that to be always operating. So if you didn't have one of those installed, well, say you ordered it without the hard drive, what IBM would do is they would put this big load resistor in the hard drive bay area, and that was connected to the 12 volt rail, I think, maybe even the 5 volt rail, I think just the 12 volt rail, and it would simulate the load of the hard drive, which was missing. And they had to do that because the power supply apparently wouldn't work reliably without that load. Now, the funny thing is mine does not have that big load resistor in there. So maybe that's not the original power supply, because when I got that thing, it did not have the original motherboard, and it actually had a 386SX that someone had put in there, and the original large hard drive was removed, and it had a It had just a little small half-height drive. And right now that hard drive has been removed and I'm just running a compact flash card. And that thing works no issues at all. But the fact still stands that a lot of these old power supplies, especially like the ones on the Apple IIs, they do not work properly if they don't have a load. And typically, if you turn them on without a load, you either get really high voltages coming out of the DC jacks, or the power supply won't run properly. Like it'll just click, 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 click as it tries to restart. Switch mode power supplies, which of course is what this is right here, has regulation with a feedback circuit, and it can detect if the voltages go too high. And there's a range of adjustability on the feedback circuit. So it can only handle so much out of tolerance of the output voltage where it can compensate for bringing down the output voltages. And it does that by manipulating the switching frequency, or there's a couple different methods for it. But if it exceeds that ability for it to adjust and it's registering something like 7 volts out of the 5-volt rail, it might freak out and just shut down to try to protect the computer that's plugged into it. Modern power supplies have a bunch of safety circuits in them, over current protection, over voltage protection. These old ones aren't always as fancy as that. So they can't always detect if you have overcurrent, like a short circuit on these rails. Although I'm pretty sure the high quality ones can do that. And that's why if they can't regulate the output voltage, since it's too high, if you don't have the load on there, then it might just shut down. The reason why I'm bringing all that up is with this power supply, since it's an older one, I'm not convinced if I just plug this in and turn it on and I don't plug anything into the power supply that it's going to work properly. It might just not run, and it might make you think that the power supply is bad and you might toss it out or recycle it. And the other thing is that's scary is you don't want to necessarily just plug this right into a motherboard without load testing it first, because what if there is something wrong with the regulation on this and it's outputting 7 volts or 8 volts on the 5-volt rail, or something completely out of whack like that, which could damage your hardware. So that's where this electronic load comes in. This load here, sorry, I can't really show it very well. It's a Dingchen DCL6204. Essentially, it's a dual channel electronic load, so it has input 1, input 2, and you can set this up as an on-screen display. And we can say, hey, on input 1, say we want to pull 1 amp on this one. And on this one, we want to pull 1 amp as well. And we'll hook the 5 volts up to this, the 12 volts up to this. And on the screen, when this thing starts running, it'll actually show you the amount of current that's being drawn, the power, which is watts, and then it will also show you the voltages of each of the rails. So it's a very handy little device because you can vary the load, you can turn it up, you can turn it down. We can also let it run for a while. You can even program this thing to like ramp up the load, ramp down the load, have transients and stuff like that. It's all relatively fancy, but this is a perfect device for hooking up to a power supply like this because we can control that load. And it says right here, I can't really read it, but it says 150 volts / 20 amp. And this thing can do up to 400 watts, I think, total. And it does have a cooling fan inside on the back there, somewhere in there, start cooling it down once it starts dissipating a bunch of the load. And that's how these work, is they have some transistors to dissipate the load. But no matter what the voltage coming out of this is, it won't damage this device because it is good for up to 150 volts. So if there's some terrible short inside of here where mains ends up coming out of these connectors, it's not going to damage this, but it would totally, absolutely damage a motherboard if I plugged it in. Now, you may see on some channels that people load test a power supply by hooking up something like a hard drive or a few different hard drives. The problem with that is these hard drives draw a good amount of load on the 12-volt rail. I mean, not a ton. Is it written on here what it draws? Yeah, 12 volts, 250 milliamps, 5 volts, 275 milliamps. The startup sequence, when the drive is spinning up, that actually draws more of a load on the 12-volt rail. But the problem is it's just not a lot of load. And almost certainly, on these power supplies, it's the 5-volt rail that is the most important one, and often it's the only one that's actually regulated. The other rails, and we can see the different rails this thing has, it's got 5, 12, -12, and -5. Well, if 5 volts is regulated, and that depends on the amount of load on the 5-volt rail, then the rest of those are just derived from the 5-volt rail, meaning the transformer that's in here, which is used to convert the mains input voltage, which is converted to DC and then chopped down to these different voltage rails. It does this via different taps. Well, the thing is, if the 5 volts regulated and you have some load on there and the 5 volts is running nice and happy, well, typically the 12 volts is going to be around 12 volts. But if you're drawing a heavy load on the 12-volt rail and nothing on the 5-volt rail, well, 5-volt might float up to 7 volts because there's no load on it, and then the 12 volts might be at 15 volts, or different things can happen depending on how the regulation works. And you can never really tell by just looking at the outside of the power supply. And even looking at the inside, you can't always tell unless you have the schematics. Now, this power supply breaks up the actual load capabilities per connector, which is interesting. 4 and 5 are actually these ones. It's labeled. I don't know why someone wrote 6 and 5 on here when it's really 4 and 5. But these are the ones that go onto the motherboard, and these contain all the various rails, including the power good signal. So it's saying here that these wires can supply 3.8 amps on 5 volts, 0.7, 12 volts, 0.3 on -12, and 0.3 on -5. The minus rails are pretty much never used for any kind of load on computers. They're just used as like bias voltages or maybe to run serial ports. There are a total of 4 5-volt rails, and each one can supply 3.8 amps total. Now, it doesn't actually show us what the total amperage is supported on the 5-volt rail. Inside this power supply, all of these red wires, which is 5 volts, are connected together. But for some reason, this one on P1 is only good for 1 amp, and then these are good for 1.8 amp. And I don't really get that. These are the ones that go to the drives, the Molex connectors. And the wire gauge itself feels the same as the ones that are going to the motherboard connector. So I don't really get why the current rating is lower. And why is it lower on one of them, P1 versus 2 and 3? I kind of have to assume by looking at this, and I'm not 100% sure about this, that the maximum current the 5-volt rail can supply is if we add up all of the 5-volt rails on all of these connectors. Now, you wouldn't want to just draw that maximum from one of these wires, even though I think inside the power supply they're all connected together on the motherboard. You would really want to spread that load across all of them. But to give this thing a maximum load test, what we'd want to do is comment all the 5-volt rails together and then run those into the electronic load. And the electronic load, I'm just looking at it right now, 20 amp is its maximum current draw. So I think that would work for this power supply, 20 amps if we add up all the 5 volts. Yeah, that's 19.8 amps for the 5-volt rail if you add up all of these together. And then if we add up all the 12 volts, we have 7.3. And there's really no point to load test the minus rails. Those are usually just derived off a secondary winding and a little voltage regulator that's inside the power supply. You can just check those with a multimeter. Now, as I was saying, the problem with using a hard drive is it may not satisfy the minimum requirement for the 5-volt regulation. So I really don't recommend hard drives as a good load source for these older power supplies. And I really recommend that you should load up both the 5 volts and the 12 volts with a good amount of current. Now, one thing in the past that I've done before I had these electronic loads is I used these light bulbs that I had from cars. And all I did is I took an old clip lead, cut it in half, and then I just quickly soldered the wires directly onto the bulbs. And I also bridged the 2 contacts because these are dual filament bulbs. I think, well, actually, I don't know why these are dual filament and they're orange. Like, you would think if these were white, they'd be a brake light and a combined running light. Although, if you have a red brake light and you put orange bulbs in there, it's totally fine. Just unnecessary white bulb would work. Either way, these are 12-volt bulbs, so they will present a good load on the 12-volt side, and I'm not sure what they'll do on the 5 volts. They actually do light up. I'm just not sure how much load they actually present. The positive about using bulbs as load testers is they are cheap. You probably have these in the drawer or something like that. The negative is they get very hot. So if you just leave them on the bench and you let them run for a while, they can burn holes in your mat or burn your desk and leave little burn marks. The good thing about DC loads like this is, of course, like I said, they have a fan, they don't get excessively hot, they can do all sorts of stuff. They can show you the voltage, the current that's actually being drawn. You can adjust it on the fly. The negative about these is they are not cheap. So I don't recommend getting one of these unless you regularly need a DC load. And in that case, you could just use light bulbs. In fact, if you go to the junkyard and you buy a bunch of light bulbs out of old junk cars and the little sockets, you could build a little board and install a bunch of light bulbs, measure the current, and then you can put little switches on there so you can switch in and out the light bulbs. Plus they won't be burning your desk by just sitting on the desk with this because they're in the holders. And that's a great way to have a nice DC load, or AC load for that matter, but a good DC load for power supplies. And if you write down the current of each light bulb at each voltage, then you could just switch them on and off and just clip on the right amount of light bulbs you want for the exact load you need. And that's a nice, inexpensive, home-built way to create a DC load. All right, so that's enough talking about what I'm going to do. Let's open this thing up and take a look inside. I know it's going to be quite gross in there because this thing was from a machine that was full of cigarette smoke, dust, and very stinky. And in fact, the outside of this had a real, I don't know, tarry coating on it that was quite gross. So I actually spent a good amount of time to kind of wipe this down, because every time I touched this thing, my hands were sticky and nasty. Now, I've never taken apart one of these Astec power supplies, so do I know exactly what to take out? I do not. So I'm just going to take out screws until I can get the top cover off. Now, incidentally, I've had a few questions about what this is. You know, this is the input, the IEC power input, but what is this? That is just a pass-through that goes through the switch. On some older computer monitors, they actually, instead of having a normal plug that would go in your wall, it would have this connector. And the idea was you plug your monitor into the power supply, so when you turned on the entire power supply with the computer, it would turn on your monitor. And these will be really common for people who live in Europe, because a lot of time UPSs will have this as the power output as opposed to a normal plug. But you can get power cords just like this, and that you can plug that into there, and then you can plug this into the back of your monitor if it doesn't have a permanent power cord. Of course, you can also plug it into here, and now we'll get infinite power. No, I'm just kidding about that, of course. Okay, I think I've got all the screws out. I'm trying to figure out how this works. Looks like this part of the cover slides this way towards me. Yes, it does. In fact, it probably does it this way. Here we go. Okay, well, we're looking at the top side of, I think, the power supply itself. And this is a 2-board design. Fancy. My intent here isn't to do any kind of massive testing on this. I just want to inspect, make sure everything looks okay. Like, I don't see anything. Also, I'll look for refills, but I don't see anything bad. Caps that are like bulging or obviously leaked or whatnot. And then potentially I'm going to go outside and blow out the dust, because you can see I did already blow out some dust, but the fan looks pretty gross, although it seems to spin pretty nicely. All right, so first off, there's this board on the bottom. Almost certainly, this is the board that converts your mains input into high voltage DC. These switch mode power supplies only run on high voltage DC. They don't take the AC. The AC has to be converted to DC first, and that's what's going to be happening on this board. Notice it's got this package. That's a big bridge rectifier. This choke, we have some filtering going on. In fact, these caps, these blue caps, will be where there could be refas on this board design. You can tell because these are X2 caps, which are the same as what refas are, but these are the type that don't basically have a problem when it, like a refa does, that is. But I don't know what rhyme or reason there is for power supply manufacturers to use these types versus refas. So these could have easily been refas, and in that case, I'd have to take this thing apart and change those out. Now, it appears getting this board out is a little tricky. There's a fastener there, but it's, you know, through the top. So I think the way it would have to come out would be this top board would need to be removed. Looks like you have a couple fasteners here. I'm just going to see if this comes out relatively easily, or what exactly we have to do to get this out. Okay, so those are out, and now this board is somewhat loose. Now, part of the issue is the cable gland right here that's holding these cables in. These are kind of tricky to get out. You need a special tool really to get this out easily. And obviously, without getting that out, this board isn't going to come out very easily. A very nice viewer sent me the right tool to get this out. So this is a Pros Kit CP311. And this allows me to clamp this down. And there we go. And with this gland, I can squeeze it, twist it, and pull it through. And once I've done that, then this is easy to open up like that, get it off, and then the cables come through. And now we can slide this out. We should be able to, at least. Okay, so it looks like it's held on by this bracket there. Part of the issue here, the fan was connected. That obviously came off. I didn't unplug that. Whoops. There's also some connections for the high voltage DC down to that lower board. So how does that connect up? Okay, well, it's actually soldered, so there's no connector. Is there a connector on the other side? No. Well, that's pretty rude, but I guess that's fine. This comes out enough so I can inspect it. Now, the fan connected right there to the board. I bent those pins a little bit, so I just bent them back. And now's my chance, though, to kind of inspect, make sure nothing looks like it's damaged. I don't see any burned resistors, bulging caps, but I wouldn't expect to, because again, ultra high quality power supply, everything looks totally fine. From a topology standpoint, as I mentioned, the mains input comes in on these wires. There's a fuse. This is all filtering, bridge rectifier. These are the DC high voltage caps that essentially create a nice stable DC voltage that goes into this power supply. And since this thing is a multi-voltage one with a switch, I know how this is hooked up because I've talked about this before. Essentially, when you set it to 120 volts, it actually wires us up in a certain way that it does a voltage doubler, and that these capacitors are actually always going to be running at the same voltage as if this thing was already running on a 240 volts mains input. Or actually 250 in the case of my house, because I have about 200 or 125, 126 volts mains all the time. The high voltage DC makes its way over to the main power supply on these wires, and this whole section is the driver circuitry and the switching transistor, which is this part right here, for this transformer. This is what's converting the high voltage to low voltage. This is all the low voltage side over here. Instead of an optocoupler for feedback, this is using magnetic feedback, which is basically like a little transformer. So this has to create an AC waveform that comes back to this, and this influences all this stuff here, like that chip and these components and whatnot. If we flip this over and take a look at the back side, you can see the isolation distance between the high voltage side, which we know is this side, and the low voltage side. And this has a little isolation slot there. It's a little piece of plastic or fiberglass that helps make sure we don't have any arcing between the high voltage side and the low voltage side. So there's another 6-pin package there attached on both sides. So maybe this does have an optocoupler and it has magnetic feedback. The transformer itself is what's converting the high voltage on this side to the low voltage DC on this side, which of course there's going to be multiple windings, one for 5 volts, one for 12 volts, one for the negative rails. And if we flip this back over and we take a look here, I'm assuming this is a choke. This is the output filtering for like the chopped AC signal. It gets converted back into DC using some diodes, which are probably these packages that are on this heatsink right here. This section over here has a little IC, bunch of components. And on this board, we have another IC, which could potentially be some additional voltage regulation. Let's see what it says on it. Astec computer, 1985. Yeah, can't really make out what's what. But part of this is probably going to be the overcurrent protection or the overvoltage protection circuitry as well, which can like shut down the entire thing if it detects anything out of the ordinary, like any load imbalance or voltage out of whack, then it can tell this side of the circuitry to shut down the entire power supply to keep it from running. Now, when you have one of these open, and I'm looking at this and I don't see any issues, a couple things you really need to look for is if you have any small capacitors that are near hot items, like power resistors like this, those can often be failure prone. And here's an example. There's a little cap there. It's pretty close to this little power resistor. I don't know how hot this gets, but if this power supply is having issues starting or running or being stable, then I might go and look to replace that capacitor and this one, since that's also relatively close to this hot thing there. Over here on the output side, they're far enough away from this hot thing here that I wouldn't necessarily think there's a problem. Not to mention this is right where the fan is. So almost certainly it's probably fine because it keeps that area really cool. This section over here is further away, so these components might get hotter. There's also these electrolytics over here on this side, which has to do with the other voltage rails. And we need to make sure that those look good, but nothing is bulging. I don't see any leaking whatsoever. And one thing that you can also have is potentially cracked solder joints. So you do want to kind of inspect for that. Anytime you have connectors that go up to that little PCB, that extra one that's right over here, you could have cracks there that could keep this thing from running. So I'm just going to spend a moment to kind of inspect, and I'm going to reflow anything that looks out of the ordinary. Oh, and incidentally, remember how I said all the 5 volts and 12 volts were just parallel together? Yep, that's everything right here. In fact, looks like this is the 12 volts. This is the ground right here, all these connections, and that is the 5 volts. It is all just parallel together. So it's funny, on the top of the power supply, I had those different ratings. I mean, there's no real reason for that because this is all just common together. There's even an extra hole in the PCB right there for another 12 volt wire that just isn't fitted. And when it comes to power good and like the negative rails, that's a connection, that's a connection. And I think this is the connection right here, maybe for power good actually, right there. So these I think are minus rails. That connection looks cracked right there. See how there's a little bit of a ring there? That's what a crack looks like. Not to say that would cause a problem. I mean, this is a low load connection. There's not a lot of power going through this, but still, that's what you want to look for, stuff like that. All right, so I'm going to spend a moment to inspect. I'm going to reflow anything that looks suspect, and then I'm going to take this outside and hit it with compressed air to try to get all this crap off of it. I reflowed a few joints on here, and I just used the vacuum cleaner to clean this up a little bit. I haven't yet taken it outside to dust it. I thought I would check a few of the capacitors in circuit, just these little guys, to see what they look like. Okay, I'm having trouble reading that one. I know I'm giving up on using those tweezer things because sometimes I struggle with those. These are really pointy, these tips on these multimeter probes, and I can just get more accurate results out of them. Okay, we're getting 41 microfarad. Now, I'm in auto mode, so I can't look at the ESR, but it has a D value that goes up the worse the ESR is, and that 0.3 is actually okay. So let's see, 41, and that's at 1 kilohertz. What is this little cap? It's a 47. So that cap is actually fine, no issues whatsoever. Now let's check this other cap right there that's near that heatsink. Those are the two I'm the most concerned about because they're little. Let's see what this one reads as. 0.2 on the D value, it's a bit lower, 47 or 46 microfarad. And what is that cap actually? That's also 47 microfarad. Okay, so both those caps seem totally fine actually, no issues. So it kind of tells me that I don't think there's kind of any real problems with this power supply that I suspect, at least. There's no obvious issues. If you really want to double check stuff before you even turn it on, you would test all the semiconductors, so that's all the diodes, there's a bunch of diodes all around, and the transistors for shorts. Sometimes though you can be tricked because the transformer will appear like a short if you have diodes across inputs and stuff like that. But generally, you know, the ones over in the regulation circuit here, those should not show up as shorts. That reminds me, I don't actually see any kind of adjustment potentiometer for the voltage regulation at all. Could be a little package on this board that presents like a 5-volt voltage reference, kind of a calibrated part, and that helps this thing compare to that using a comparator and then run as accurately as possible. All right, well, I'm gonna go take this outside and blast it with compressed air to try to get some of this cigarette stuff off. Okay, with the air compressor, that made a difference, but not entirely. And the problem is gonna be with this power supply is because it was smoked around so much, it's going to be stinky. So anytime I run this thing, it's gonna smell bad, like cigarettes. So it's not ideal, but unfortunately, not too much I can do about it. Maybe ozone generator would help get rid of stuff, but this dust is really, really caked on. But on the other hand, I got a lot of it off, so I think it's gonna be better than it was, that's for sure. What you can do is also, oh wow, look at that tar. Wipe down the insides of the cover. That's gonna help as well. I put some simple green on this paper towel here, and yeah, it's coming off pretty brown. Pretty brown. Ugh, gross, isn't that? Can't believe that's inside people's lungs. It's just hard to believe, really. Oh, wow. So now I just have to kind of get this thing back together, get this fan reconnected. What's the best way to do that? Okay, so I just got my hand in there. Now it is reconnected. And I think that's back in its proper spot. Yep, it is. Right, to put this back on, just go around the cables, the whole bundle. Just kind of get that started, and I'm going to use this tool to squeeze the gland and get it in there. Nope, not quite. These can be a little bit of a pain in the butt. There's probably a bigger tool that is better suited to this size of gland. All right, with the vice grip, I got it in. That was not easy with this tool. The smaller ones are no problem. Just bend the metal back that bent up a little bit. But yeah, there we go. That is in there properly now. So now it's time to do some load testing, but I need to figure out a way to get this connected up to the electronic load. And I'm going to use this. This is perfect because I can plug one of the Molex connectors into this, and then I can just cut off this SATA connector, because I have a bunch of those. And I can wire this into the electronic load, one for 5 volts and one for 12 volts, and that's going to be perfect. All right, there we have it. There's my little test harness. These two I had to solder on. These two were clamp on with screws. These aren't the best connectors in the world, meaning they're not the highest quality, so I wouldn't trust them to carry a heavy load, but obviously over a connector like this, we're not going to be doing that anyways. Okay, I'm going to power this thing on. Uh-oh, knocking things over on my desk. The interface is always a little funny. So channel 1, channel 2, different modes, constant current, constant voltage. We will do constant current. And because we're in constant current mode, this is where we set the current. So I'm going to do, I don't know, 2 amps on this one. And now we hit channel. And I think this one also in constant current mode, yeah, CC. So we'll do the same there. You can, oops, you can move the cursor around so we can adjust this. So I'm going to do 2 amps on both. And now when we turn on the load, now it's on for both of them. So currently I have the load turned on since that's what we want. And I don't need to use the multimeter for measuring the voltage of those 2 rails, but I can use this for measuring the other rails, the negative rails. All right, so according to the lid on the power supply, it's P2 and P3 that are good for the higher loads. So we're going to use P2, connect that up to here. Make sure that's a nice firm connection, and it is. Just make sure this is in the off position, and it is as well. And this is where things get kind of sketchy because I'm going to plug the mains into this thing, and this thing will become live. Not so much the top board, it'll be the bottom board initially. So we'll just snake this around, make sure it's set to 115 volts. It is. You don't want to plug that in incorrectly. And just so you can see this a little bit more easily, I am going to connect up to the 5-volt rail with this multimeter. And the load is on, and here we go. 3, 2, 1. And it is running. Currently we're drawing 10 watts, 10.1 watts on the 5-volt rail, which according to the load is at 5.092 volts, 1.99 amps being drawn from it. It's a little bit higher on that multimeter on this wire that doesn't have any load being pulled on it. Fan is running. And then the 12-volt rail is currently getting 2 amps of load, 23.2 watts. So we're drawing about 30 watts from the power supply right now. I actually want to increase the load on the 5-volt rail. The 12-volt rail, by the way, I didn't mention, we're drawing 23.2 watts. It's at 11.6 volts, so it's kind of low. But I think it's because it's not directly regulated. The 5-volt is what's regulated. As we draw more current on the 5-volt rail, the 12-volt rail is going to go up. So there it is. 11.6, which is actually pretty similar to what this is. But I'm going to increase the current draw from 2 to 3 amps on the 5-volt rail and watch this go up. So it's at 2 amps right now. Now we're at 3 amps. And there we go. This did go up a little bit. So we're still drawing 23.4 watts on the 5-volt rail, but we're now drawing 15 watts on the 5-volt rail, 3 amps. And let's try 4 amps. There we go. We're at 4.962 on this wire here because of voltage drop. And if we go back to the 5-volt rail, there we go, we're down a little bit, 5.096 without the voltage drop because we're going directly onto the PCB right there, while this is measuring off the voltage drop of these wires right here, and they're kind of thin. But one thing is for sure is this power supply is currently supplying about 50 watts, about 45 watts of power to the electronic load without any issue whatsoever. Now I am curious, if we turn it off, okay, it turns off. That fan is kind of an annoying fan, so I might want to change it. Luckily, it's pretty easy to change because it's, you know, right there. So you can slide it out without having to take anything else apart. Well, although you have to move this PCB a little bit because look, it has this bracket there. But anyways, I want to make sure this power supply can start with that 50-watt load right away. No problem. Goes directly into regulation. There's our 5-volt rail again. You know what I'm going to do? I'm going to hook up the oscilloscope and we're going to measure the 5-volt rail on the power down and power up just to kind of see what it does with the roll mode. So I'm going to turn the power supply off. Go put that right there so you can see it a little bit better. So we are in roll mode right now. So as I turn on the power supply, you're going to be able to see what the 5-volt rail does. It's a little bit of overshoot there. And we turn it off. There we go. It drops pretty well. Oh, that was weird. There was a little bit of a spike there. Was that on its own, or was that me? No, look at that. How funny. So we turn that back on. Turn it off. It's almost like it's trying to regulate a little bit there. And then you get a little spike, a little gasp. And now I think it's fully off. We turn that on. Notice the max, 5.2 volts. That overshoot's kind of rude, actually. The accuracy of this is not that great. So as I turn this off, see we're still at 500 millivolts, 2.5 gasp, and then it'll drop down. Pretty curious. Let's see what the 12-volt rail does. So 12-volt rail still has a little bit of output on it, 300 millivolts. Let's turn this on. Oh yeah, well, I gotta adjust this. Gotta adjust this so we can see the whole scale. Okay, there we go. So we're at 12.1, turn it off. Do we have that little gasp, that last gasp? Yep, look at that, little gasp. That's interesting. I don't think I've ever seen that. That's obviously as the main caps drain on this thing, they're still working really well. And then it's trying to regulate and it just can't, there's not enough source or input voltage, and then it just gives up. All right, does the 12 volt have the overshoot? No. I mean, a tiny bit, but nothing like the 5 volts. I wonder what's up with that. Okay, here we're on the 5 volt rail again. Turn it off, turn it back on. Yeah, we got that overshoot. I don't think it's really going to be a problem. It's not like it's going up to like, 20 volts or something like that, but it is something. Yeah, 5.8 volts according to this. Okay, so I've adjusted the current draw on the load to 2 amps on the 5 volt rail. Let's see the overshoot now. It's similar, but it's shorter. And turn off. See about that last gasp effort. Whoop. Very funny. 5.9 volts according to this. It's a little bit higher. I can turn up the load. I'm going to put it to 5 amps. Okay. Yeah, it's about the same. It seems that spike that happens doesn't really seem to be load related because we're drawing 25 watts right now from the 5 volt rail, 5 amps, which is typical. I think that's kind of what you would maybe get on whatever computer we plugged into this thing. And well, let's turn down actually I'm going to turn off the 12 volt rail entirely. So did that really have much of an effect on the 5 volt rail? If anything, it's on right now. I turn it off. It's a little wobbly. I'm not really seeing that wobble on the load itself though. We're still drawing 25 watts from the 5 volt rail. It's at 4.827 after the voltage drop, but we see the wobble on there. But when I turn this on, 5 volt actually goes up a little bit to 4.912 volts. And it's not really changing or anything. All right, so here's the big test. I'm going to turn this off. I'm going to shut down the loads altogether. That's interesting. So that last gasp, because there's no load, kind of went up, and then now it's slowly fading. What will happen with this power supply if I turn it on with no load? And we're obviously looking at the 5 volt rail here, and I will turn this off quickly if something goes wrong. 3, 2, 1. Okay. So it went up to 7.2 volts and immediately shut down. The fan never started. Let's try that one more time. Yep. So this power supply does not like running without some kind of a load. And I'm going to turn on the 12 volt rail load only, and let's see if it can run now. Nope. So it can't run with just 12 volts. It really needs a load on the 5 volts. So the 5 volt rail load is on, and there we go, starts right up. Okay, so that's a little example of like the power supply that does not work with no load, and you really do need some kind of a load going into it to do any kind of testing. Now, for reliability standpoint, I should just leave this running like this. The fan is blowing on these wires, so luckily nothing's really getting hot. I'm drawing about 50 watts from the power supply, so about a quarter of its rated load. I could go higher, but I don't really trust these connections. I need better connections to draw more from this. Like I would need to have multiple of these adapters so I could plug all of these Molex connectors in simultaneously, and then I would feel better drawing more load on this, closer to the rated max of the power supply. What we should do is take a second to check the minus rails. So let's do that real quick. So I'll stick this probe into the ground on the Molex just because it's easier. Okay, so we're going to test the orange wire first. Minus 5.05 looks really good. I wouldn't be surprised if there's a voltage regulator that generates that. So I don't think that, I mean, it probably comes off of the minus 12 volt rail and it's regulated down to minus 5. And on this connector, the blue wire is probably the minus 12. Yep, minus 11.9, so totally fine. And then the white wire is power good, which I think should be a 5 volts when the power supply is operating normally. So that will stay low. It'll stay around ground when the first thing turns on before it starts to stabilize, and then it will turn good once it instructs the computer, hey, you're good, come out of reset, start executing code. Of course, the fact that this has a little bit of a voltage spike when you turn it on, not wonderful, but it's not like it's going that high. I mean, at least according to the roll mode. What about the smell of the power supply? Oh, it's smoky, all right. Yeah, that's not great. It's not like the stink is emanating really badly, but absolutely the airstream, the smell in there, yeah, it's a bit smoky. Okay, I think what I'm going to do is I'm just going to leave this here for 10 minutes. It's already been running for 202 seconds. In fact, I'm just going to turn this off and I'm going to reset this because there's a timer on here. Oh, actually, how do you reset the timer? Okay, if I just change the load amount, it changes the time. Okay, so now we're at 0 seconds. Turn these both on. Turn this on. So 5 amps on 5 volts, 2 amps on the 12 volts. So 50 watts thereabouts. And I'm going to let this run for like 10 minutes, make sure this power supply is okay and happy. All right, so the power supply has been running for about 5 minutes, and I was curious. I turned it off and on with this set to single shot mode. I wanted to see this overshoot a little closer up. So I've adjusted the time base. We're looking at 5 milliseconds per division, and it seems that it actually goes up to about 5.4 volts because I have the 2 cursors set up. So this one's set up on the ground there, and then this line here is at the top of that peak. So we're hitting about 5.4 volts before it settles back down. And that is a lot less scary than 5.8 volts. And if we go back to kind of where it settles, like there, 4.7 volts. Oh, that's kind of interesting. I think I did a measurement problem where I didn't let the power supply settle enough while it's turned off, because you know it has that little last gasp thing. So I'm going to turn this off and we're going to do this again on camera. So I'm just going to let this thing settle for a while until I see the voltage on the 5-volt rail on this at 0 volts, because yeah, currently it's still outputting 0.4 volts on both rails. Can probably help this by shorting together the 5-volt rail here with a clip lead. Okay, so 0 volts. Okay, everything's at 0 volts now coming out of the power supply. All right, so we set this to single shot mode, so it's waiting. Okay, here we go. 3, 2, 1. There it is. Okay, so the bottom line, I'm going to move it on top of the trace, like so. And this one, we'll move this up to the top of the peak. Ah, okay, 5.8 volts. Now, each one of these divisions is 5 milliseconds, so you have to think that this is probably over voltage for maybe about 15 milliseconds or so, which is not insignificant. This is not a super short transient. This is something that happens for, longer than I would like. Is this normal or fine? Probably. Yeah, probably is. I think what I'm going to do is I'm going to grab my usual ATX bench power supply that I do my testing with, and we can kind of compare that spike. This USCAN 350 watt ATX power supply is a Pentium 4 era supply, so late 80s or late 90s, I mean, and I have replaced some of the caps in here because I did have some issues with them. Incidentally, this power supply has 35 amps on the 5-volt rail and it has 12 amps on the 12-volt rail. So it's not suited to more modern computers that need a big load on the 12-volt because of all the voltage regulation. This gives a lot of current on the 5-volt rail, which is Pentium 4 era or earlier, which is why I like this ATX power supply. Oh, and it also has -12 and -5, which later ATX power supplies don't have. Okay, first off, this is on. This is on. Let me turn it on and just look at the load on here. Okay, it's running, no problem. We're drawing about 50 watts, just like we were with the other power supply. Let's check a couple of voltages on this. Okay, 5-volt rail at 5.108, seems fine. And then our 12-volt rail, 12.1. And obviously it's a little bit lower on the screen there just because of the voltage drop. So I'm just gonna go back to roll mode, I think, because that just gave us the accurate info anyways before. So we switch this to auto mode, put this into run mode, and we just increase the time base until this switches to roll mode. There it is. And there's our 5 volts. Turn that off. No last gasp on this thing. Turn it on. A little bit of overshoot there, but not a lot. So max is 5.2. Let's see what that goes to. 5.3. Okay, so the overshoot on this is much less than that other power supply. Let's check the 12-volt rail overshoot. Okay, so that's 12 volts. There it is, 12.4. Turn this off. Turn it back on. Yeah, pretty much no overshoot. Well, now this kind of makes me want to check out other power supplies. I think I have some old stuff floating around. We can kind of look at that overshoot stuff. Okay, here's a real chonky boy. This is a leading edge MP2400L power supply, and it's got adjustable 5 volts. I have tested that back in 2023. Let's get this plugged in. I have it plugged into the load. I'm just going to turn this on, make sure that it works. Yep, that fan is quite noisy, but it's drawing 50 watts right now. No issues whatsoever. Let's get this thing hooked up so we can see what it looks like on turn on. Okay, so there's our 5-volt rail. Here we go, 3, 2, 1. A little bit of an overshoot, but not much either, about 5.3, same as that other one. Turn it off. No weird last gasp on this thing. And how about the 12-volt rail? So there's a little bit of voltage sitting on there. Change it to 2 volts per division. No overshoot. So that looks good. Back to our 5-volt rail. Oh, sorry, that's just a bad connection on my part. I'm just holding the probe into the Molex connector. Here we go. Huh, that's odd. So I guess it was still shutting itself down. I need to let it kind of wait a little longer. Here we go. Huh. So it ramps up. So oddly enough, on the output, I see 5-volt rail has nothing on it. Oh, now it's got, so there's a little last gasp there. I'm going to short it while everything's off here just to kind of drain it down to nothing. And we'll see if that comes back. Okay. Okay. There's still a little bit on the 12-volt rail though. That's interesting. So it's got some beefy caps. There we go. Okay, it's all down to nothing now. Let's see if that overshoot comes back. Yeah, it did. But only 5.3 volts. Very interesting. Now I have to admit, this is not a test I've ever done, so I don't really know if one power supply is worse or better than another. And I don't know if my 5170 power supply does this, but certainly so far the ATX and this one don't. I mean, the overshoot is so minimal, it's not that 5.8 volts. So I don't really know what to think about this. If you have experience testing these in a similar fashion, let me know what you think about the overshoot that this thing is doing and if that's a problem. Is this faulty? Is this safe to use? These are all questions I have. I mean, I would err on the side that this is probably fine, even doing what it's doing here. But I don't love the fact that it does spike up to 5.8 volts, albeit briefly, and then settles back down. And that's even with a 25 watt load on the 5-volt rail. So yeah, let me know what you think about this. And I mean, the fact that leading edge power supply, by the way, is just as old as this. I'm pretty sure it's from the 80s because that was a 286 machine. This is from a 286 era machine as well. And it does that overshoot. And I just don't love it. And I wish there was a way to kind of turn down the regulation. It's a bit hot on this, meaning like the 5 volts is always a little bit high. I mean, coming out of this thing, it's like 5.2, 5.1, 5, something like that. It's a little hot. Obviously, if we turn that down, then that spike would be less as well. But even if we turned it down to 5.0 volts, it would still spike up to, 5.7, 5.6 and a half, which seems a bit high as well. So yeah, let me know what your thoughts are on this. I'm kind of surprised. I'll probably put this thing back together and just leave it on the load for maybe an hour, let it run and really go, and then I'll test again. And if there's any change, which I doubt there will be, I'll put an update down below in the comment section. I'll pin a comment. But this is kind of surprising, and I'm not sure whether I'd want to trust this. That's one thing I wanted to mention that I tested while I was running the power supply after I finished recording the footage for this video. I hooked this thing up to my kilowatt, and I noticed that while I was drawing exactly 50 watts of DC from the power supply was drawing 83 watts from the wall. That's an absolutely atrocious efficiency of about 60% if my calculations are correct. I also tried increasing the load and decreasing the load and didn't really change dramatically. So yeah, this power supply, well, I think it's just common for old power supplies. Efficiency sucks. Modern power supplies, you can be reaching into the 90% range for efficiency. Now, by the way, I'll add this one thing before we end. One thing you can do with these types of power supplies, if you have one of these and you're having issues with the original power supply, there's nothing wrong with me taking one of those ATX power supplies, the ones with a good 5-volt rail, and transplanting the guts into this. You might have to build a little bit of scaffolding to do it, mount it up properly, but you could mount that ATX power supply in here, and I have done that. I have an old compact power supply that I could not get working. It's switch mode power supply, has a very complex circuit to check that it's working properly, and there's no schematics for it. I could not figure it out. It would just shut itself down. So I put an ATX power supply inside, and it's an old compact Desk Pro, and the computer works perfectly with the ATX power supply in there. I just hardwired it so the ATX turns on as soon as the power is applied. I also have an ATX power supply in my TRS-80 Model 3 because its power supplies were broken and I didn't know how to fix them back then. I still have those power supplies and I do know how to fix them now, so I can get those working again. But the ATX supply has been totally fine, and it's just sort of tucked in there. It's a little thin ATX power supply and it works. Now, in case you're thinking about putting a Meanwhile power supply in here, you can't do that because you don't have the power good signal, and you need that to be working because the motherboards do require that. If you're just powering up like hard drives and stuff, you don't need it. But for motherboards, you need power good, plus those negative rails. So, but an ATX supply, like Pentium 4 Aero one, which you can still get at e-waste places, stuff like that, if it works, maybe you have to recap it a little bit, that'll be a perfect thing to stick in here. Anyways, I don't know. Very surprised that it's doing this overshoot thing. Otherwise, it's working really well. Nice and stable power. Regulation seems good. It's a bit smoky. But I think I'm going to write a note on here for now that just says spiky, do not use, or caution, or something like that, just to kind of refresh my memory about this thing in the future. So if you enjoyed this video, thumbs up. If you didn't, you know exactly what to do. Thanks for watching. A huge thanks to my supporters. Name go up the side of the screen, make it possible to do this full time. All the usual YouTube stuff, thumbs up, thumbs down, comment down below, the usual stuff. And that's going to be it. And just a reminder, I'll be at VCF. There's a few VCFs coming up that I'll be at. I'll put it on the screen right here so you can see which ones I'm going to be at. And I guess that's going to be it for now. So stay healthy, stay safe, and I'll see you next time. Bye-bye.